Hello friends, welcome to engineering tutorial. So in this video we are going to discuss some more concepts on resistance and resistive circuits, which is Kirchhoff's voltage law and Kirchhoff's current law. So Kirchhoff's current law, it states that the algebraic sum of currents entering or exiting a node, it depends which sign convention you attach to what. So the algebraic sum of currents entering a node or exiting a node, that is equal to 0. Okay, so here, so suppose we take a particular node. We have, let's say, 3 pathways which go out and 3 pathways which go in. This is the node. So this is I1, this is I2, this is I3, all directed inwards. So this is, let's say, I4, this is, let's say, I5, this is, let's say, I6. So here it means the sum of the currents which are entering the node, that will be equal to 0, and it will also be equal to the sum of currents exiting the node, this, or the net currents entering and exiting, that will be equal to 0 if we do it like this: I1 plus I2 plus I3 minus I4 plus I5 plus I6, that is equal to 0. The total summation of currents, that is equal to 0. So here one thing you have to take care of is that you attach one particular sign convention for current entering the node. You can either take current entering that node as positive and current exiting the node as negative. You can do the reverse also, that is current entering the node as negative and current exiting the node as positive, but you have to always stick with that one thing, don't change it. Okay, if you are taking current entering the node as positive, then you have to take current exiting the node as negative. If you are taking current entering the node as negative, then you have to take current exiting the node as positive, and you have to stick it throughout the whole problem, don't change it. So this is KCL, and KVL is same thing for voltage, that is the algebraic sum of voltages or voltage drops around any closed path or loop in a circuit, that is equal to 0. So here if we take this closed path consisting of resistors R1, R2, R3 connected across a voltage V, a current I flowing through it. So here the KVL, it can be expressed as V is equal to V1 plus V2 plus V3, or V minus V1 minus V2 minus V3, that is equal to 0. Okay, where V1, V2 and V3, they are the voltage drops across R1, R2 and R3. Okay, so V1 is equal to IR1, V2 is equal to IR2, and V3 is equal to IR3. Okay, that is the thing, and you have to pay attention to what sign you use. So here I have used the second sign dominating method. So by that I mean, while applying KVL in a particular direction, whether it is clockwise or anti-clockwise, I have always used the second sign that is coming. Here the second sign is positive for the voltage source, and for the voltage drops the second sign is minus. That is my style of writing KVL. I always write KVL equations in that way. So it basically, the KVL equation is like this: second sign is positive, okay, so plus V minus V1 minus V2 minus V3, summation of voltages, that is equal to 0. So this brings V is equal to V1 plus V2 plus V3. Okay, This is the thing. You can also do it using the first sign dominating method. In that way it will be like this, where you pick the first sign. Okay, so using the first sign dominating method, you always pick the first sign. Here the first sign for the voltage source is minus, here it is plus, plus, plus. So it will be like this. Here I am writing minus V because the first sign is minus, then plus V1 plus V2 plus V3, that is equal to 0. So here also you will get V is equal to V1 plus V2 plus V3. So here also you will get the same result. Any way you go, you will get the same result. Also if you do the anti-clockwise thing, you will get the same result. Okay, so this is KVL, and similarly KCL we can do. So here current is flowing I. Okay, this is the node where the current entering is I, this current, and the current that are going away, they are I1, I2 and I3. So the sum of currents, on one side we pick I, the current entering the node, I am taking that as positive, and the current exiting the node I am taking as negative, that is I minus I1 minus I2 minus I3, that is equal to 0. That implies I is equal to I1 plus I2 plus I3 at this node. Again at this node, current that are entering the node, they are I1, I2 and I3, and the current that is exiting, that is I. So again I pick current that are entering the node that I am taking as positive, so it is I1 plus I2 plus I3. Current exiting the node, capital I only, minus I, that is equal to 0. Summation of current entering and exiting the node, that is equal to 0. So that becomes again I is equal to I1 plus I2 plus I3. Same result. This way at the two nodes. And if you take the opposite convention, where you take current entering the node as negative and current exiting the node as positive, then it will become minus I plus I1 plus I2 plus I3 is equal to 0. That implies I is equal to I1 plus I2 plus I3. Same way, same result you will get, you do it anyway. So that is KCL. Okay, KVL and KCL. Then another simple thing, resistors in series and resistors in parallel. So resistors are said to be connected in series if the same current flows through all of them. So here the series equivalent resistance that is given as the equivalent resistance is R1 plus R2 plus R3. Simply add them up, the algebraic sum. If there are n number of resistors connected, it will go up to n times Rn. Similarly, resistors in parallel, the resistors are said to be connected in parallel if the same potential difference is there across the ends of all of these resistors. So here the same potential difference V is there across the ends of resistors R1, R2 and R3. So here the parallel equivalent resistance is equal to 1 by R equivalent, the reciprocal is equal to 1 by R1 plus 1 by R2 plus 1 by R3, and this can go up to nth resistor plus dot 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 1 by Rn. Okay, so now we'll be discussing about the two most important concepts related to whether it is resistive, capacitive or inductive circuit from the point of view of power systems engineering, that is energy and power. So for a resistive circuit which involves only a resistor R connected to a voltage source V, here it is DC, so we'll be discussing about AC in later on. So the current flowing is I. So if the current I flows for a duration of, let's say, t seconds, then the amount of energy, which is heat, which is dissipated in the resistor, which is produced in the circuit, that is equal to E is equal to the product of voltage, current and the time duration, VIT, or If we substitute V's with IR, then it will become I square RT, and if we substitute I with V by R, then it will be V square by R into T. This much joules of heat energy or energy is dissipated in the circuit. Okay, now power in a purely resistive circuit is, or in any circuit, electrical power is the rate at which electrical work or energy is done by the voltage source or the source of potential difference to maintain a particular value of electric current in the circuit. So here the work done by the circuit to maintain a potential difference, V, to drive a current I through this purely resistive circuit, that is equal to this energy by time. So that is equal to Vi, where it is VIT by T, I square R, where it is I square RT by T, and V square by R, where it is V square by R into T by T. So the time, that factor, it gets cancelled out. So the unit of electrical power, that is joule per second or watt. Okay, so this is about energy and power in a resistive circuit. In a quick way I'm not going into the details. Okay, so this is energy and power in a resistive circuit. So another important concept related to resistive circuits, that is star to delta and delta to star transformation. So in some cases you will find resistors in a circuit or a network. You will find resistors in a circuit connected in this way. It is sometimes called the star pattern or star form. It is also called as T form, okay, and this is called as the delta form, and it is also sometimes called as the pi form. Okay, so how we can convert the star form to delta or this delta form to star? There is a formula. There is also a derivation, but I'm not going into the derivation thing. Just simply I will give the formula. So there are 3 points, 1, 2 and 3, and there is this center point in star form. And how we can convert this pattern into this form, where the values of the resistances, they are altered and they are connected in between the same 3 points, so that the equivalent resistance, that stays the same, but only the pattern is altered. So first is delta to star transformation, where we are given this delta form, where the resistance connected in between point 1 and 2 is R12, point 2, 3 is R23, and point 3 and 1 is R31. We want to get its equivalent star form, or we are given a pi form, we have to convert it into T form. Okay, that is an alternative name given to star and delta. So delta to star. Okay, so for that the formula is the value of R1, this, okay, R1, that is equal to R12 R31 by R12 plus R23 plus R31. Then R2, this is R12 R23 by R12 plus R23 plus R31, and then R3 is R23 into R31 by R12 plus R23 plus R31. So here, if you notice, a pattern is emerging. This denominator, this is constant in every conversion formula, whether it is for R1 plus or R2 or R3. This denominator is constant. Okay, this is constant. And in the numerator, only, see here it is R1. Okay, R1 we want to find out, that is this resistor value. In star we are given this delta form, we want to get the R1, R2 and R3 values in terms of R12, R23 and R31. So in R1 we have all the resistors of resistance values of delta where there is 1 in it. So here it is R12, that is the resistor connected in between point 1 and 2, and R31, the resistor connected in between point 3 and 1. Okay, so here it is, sorry, R12 and R31. So this one thing is common. Similarly, here R2, denominator is the same. Here it is R2. So here there is R12, the 2 is there, then again R23. That is the resistor connected in between point R1 and 2 and point 2 and 3. Similarly, here it is R3. Here R23, the 3 is there, and R31, again the 3 is there. So this is the formula, this quick concept which you can use. Again, suppose we are given this star form and we want to get its equivalent delta form. So then the formula is this star to delta transformation. So here this delta value, that is equal to R1 R2 plus R2 R3 plus R3 R1. So now we want to get these values in terms of R1, R2 and R3. So R1, R2 and R3 are given. We want to determine R12, R23 and R31. So R12 is equal to delta by R3, where delta is this, divided by R3. R23 is delta by R1 and R31 is delta by R2. Again, here the numerator is constant in all the cases. Okay, the numerator is constant. The only thing that is changing here is C. Here we want to determine R12. So the thing that is missing, the point that is missing is 3, which is here, R3. Here we want to determine R23, that is the resistance value connected in between point 2 and 3. So the point that is missing is 1. So here there is 1. And here it is R31, the resistance value connected in between point 3 and 1. So the value, the point that is missing is 2, which is here. So the numerator is constant, this, and only we have to include that resistance value for the point that is missing. Here it is 3, here it is 1, here it is 2. Okay, so this is how you convert delta to star and star to delta. So I am discussing this because in our upcoming discussion related to power transmission line, such arrangements can come for resistors, for inductors and also for capacitors. Okay, so this is the thing.